In this section, we're going to study the behavior of a function's graph in more detail by introducing the notion of concavity. Now, we've already seen that the first derivative will tell us when a function is increasing or decreasing, but it doesn't tell us the manner in which this occurs. For example, let's say you've got a function that you're studying and a particular segment of its graph is known to be increasing because maybe you performed the first derivative test. Well, how does it increase? Does it arc upwards or does it arc downwards? In other words, does it have any curvature? It turns out that this question is going to be answered by the second derivative of the function, and that's what we're going to explore in this section. And in order to introduce the ideas, I want to draw a picture and make a few observations. So you can see it says, consider the following graph of a function defined on the closed interval a to c. So here's the picture that I want you to think about. And like I said, it's going to be the graph of some function f. Okay, and here's the curve that we're going to look at. Just going to draw a function that increases, and then it comes down and decreases, and then it increases again, maybe to about here. And again, I'm just going to look at a segment of a curve. So this is a function that is, well, it certainly looks like it's continuous on the closed interval a to c if I label a and c on the x-axis like that. And then I'm going to actually also label one other point on the graph of the function. I'm going to call that point one that has an x value of b. Okay, so that's just a sketch. And now what I'm going to do is I'm going to pick 2 points between a and b. And there's nothing special about the 2 points that I pick, okay, except they're distinct. But I just picked 2 points more or less at random between a and b. Now both of those points on the x-axis have corresponding points on the curve. So it looks like it would be this point here and this point here. Let's just get a rough sketch of what the tangent lines at those points would look like. So that's one of the tangent lines. And then I can draw the tangent line at this point. It's going to look something like that. Okay, well, what observations can we make? Look at the slope, or ask yourself, you're not going to be able to tell me what the slope is of this first tangent line that I drew, the one above the point to the left, right? You're not going to tell me much about that slope because I haven't given you an actual function to work with, but you can at least tell me that the slope is positive, right? In fact, this tangent line looks like it's quite steep. It's certainly more than 45 degrees, so it's hard to say what it is exactly because all we could do is guess, but we can say it's definitely positive and it is fairly steep. And then if we move on to the tangent line at this point, we could ask a similar question. What can you say about the slope of this line? Well, again, you're not going to be able to tell me exactly what it is, but you can at least tell me that it's positive, right? You can see it because it's not horizontal. It's aimed at least a little bit upward to the left, right? It's not flat. That would be a slope of 0. This would be a slope of a negative number. So a slope like this is at least positive. And whatever the slope is, it looks like it's less severe than the slope of this tangent line, right? It's not as steep as this tangent line. So it looks like the derivative of the function at this point is positive and greater than the derivative of the function at this point. In other words, the slope of this tangent line is larger or greater than the slope of this tangent line. And really, there's nothing special about those 2 points that makes that happen. Really what's happening is this. As the points on the x-axis move from A towards B, the corresponding tangent line on the curve is going to keep decreasing. Right? In fact, once I move a little bit more to the right, say if I took a point really close to B, now the slope of the tangent line at this point would be negative because the line would be sloped downward like that. And so it keeps decreasing all the way until you get to this point B. So that's the first observation. On the open interval a to b, f prime is decreasing. Because remember, f prime is the tool that gives you the slopes of these tangent lines. So as you move to the right, if the slopes of the tangent lines are decreasing, then f prime is decreasing. Okay, now let's look at the similar situation over between b and c. Or let's ask the similar questions. How about that? So I'm going to pick 2 points here. And again, there's nothing special about these points. I'm picking them reasonably far apart so that I can at least have a decent chance of drawing an okay picture. But There's nothing special about these 2 points. I could replace them with any other 2 points I picked between B and C. That's what I'm not labeling them. Okay, let's look at the tangent lines at these points. So at this point, there's a corresponding point on the curve right here. And at this point, there's a corresponding point on the curve over there. So let's sketch the tangent line at each point. So I've got a tangent line there. You can't say much about it, but you can say that that slope is negative. Right? The line is oriented in the downward direction as you move to the right. But then as we move over to this point, and then we draw the tangent line here, well, that has a positive slope. And if I moved even further to the right towards C, this line would actually get steeper as this point moved towards the end point over here. If you move this point to the right along the curve, the tangent line would go with it and get steeper each time. And it'd be growing in the positive direction. So as you move from B towards the right, the slopes of the corresponding, the slopes of the tangent lines at the corresponding points on the graph will increase. So that means that f prime is really increasing as you move from B towards C. So that's what the second observation is. On the open interval B to C, f prime is actually an increasing function. Okay, and with that in mind, now let's make a couple of definitions. Now is where we're going to actually introduce the notion of concavity. So start with some interval. And just like before, this technically could be a closed interval, but typically the way we're going to apply this definition in this course, you should think of this as an open interval, as an open interval that does not include its endpoints, because that's the nature in which you'll be using this definition. Okay, so the first statement is if f prime is increasing on I, so if it's increasing on this entire open interval I guess I shouldn't say open interval because the definition doesn't strictly require that, but like I said, think of it as an open interval, but I won't write open interval here. I'll just say if f prime is increasing on the interval I, well, then we say that f is concave up. That's concave up on I. Okay, so that is the definition of concave up. And so for an example of that, consider the interval between B to C here. Consider this an interval of x values. From this point here all the way to this point here, this segment of the graph, it's concave up. It's curved in the upward direction. And the example I like to think of, or the analogy I like to think of, is if rain was falling down on that curve in that segment, it would catch the water, right? Rather than the alternative. If you look between this point and this segment of the curve, well, if water were to pour onto that segment of the curve, it would just fall off the edges, right? It would just drip down the sides. So that's an example of concave down, which we'll define in the second line. So if f, and the way we'll define that is this in a similar fashion. We'll just say if f prime is decreasing on I. And then what that means is that f is concave down. Now, as you can see, a function's not going to either be concave up or concave down. It's not a dichotomy. Rather, what you will typically do is you'll just look at a function and you'll try to break it down into a whole bunch of segments, each of which of the segments is either concave up or concave down. So in this case, in this example, this curve is broken up into two. You can think of this as two pieces. It's this piece here between A and B, which is concave down, and there's this other piece that between B and C, which is concave up. Okay, so how do you find these intervals? Because in general, you won't have the picture, right? So, and really, what we're building towards is we're going to use the tools in this section to actually come up with the picture. So we can't assume that we're going to have graphs available. So how are we going to determine the intervals upon which, say, some given function is either concave up or concave down? And this comment here really answers that question. To determine the intervals of concavity of a function, we may apply the increasing-decreasing test to its derivative. Because really, it comes down to this. If you want to know where the function's concave up, you just want to know when the function's derivative is increasing. Well, we know how to tell when a function is increasing. Look for when its derivative is positive. So apply that to f prime. If you want to know when f prime is increasing, look for when the second derivative of the function is positive, right? Or in other words, the derivative of f prime, right? So this is where the second derivative is going to come into play. And then if you want to find where a function's concave down, you just want to find the intervals where its derivative is decreasing. So in other words, when the derivative of the derivative is negative. So in other words, when f double prime is negative. So that's the strategy we're going to use. We're going to look at the second derivative, and we're going to analyze it in a manner that's kind of analogous to the way we analyzed the first derivative in the previous section. Okay, and the examples that we're going to look at are here. So this says investigate the concavity of the functions. What that means is just to determine upon which intervals is the function concave up and which intervals is the function concave down. That's what you're really looking for when you hear that phrase, investigate the concavity. Another phrase that you'll hear, and you'll see it in this course, is determine the intervals of concavity. That means the same thing. Okay, and basically if you ever see a question like that, you're just going to do exactly what we do for these examples. Okay, so there's part A and part B. We're at the bottom of this page, so we'll start this on the next page.